sklearnpreprocessingMultiLabelBinarizer. Description: the multi-label binarizer is a transformer that converts a collection of multi-label samples into a matrix. Each sample is represented by a binary vector, where each element indicates the presence or absence of a specific label. Inputs: why this is a list of lists, where each inner list represents the labels associated with a single sample. Outputs: why bin this is a 2D array of shape n samples. N classes, where each row represents a sample and each column represents a label. Each element is 1 if the label is present in the sample, and 0 otherwise. Steps: the multi-label binarizer first determines the unique labels present in the input data. It then creates a mapping between each label and its corresponding column index in the output matrix. For each sample, the transformer iterates over its labels and sets the corresponding elements in the output matrix to 1. Metrics: accuracy. This metric measures the proportion of correctly classified samples. Precision: this metric measures the proportion of true positives among the predicted positives. Recall: this metric measures the proportion of true positives among the actual positives. F1 score: this metric is the harmonic mean of precision and recall. Visualization plots. Confusion matrix: this plot shows the distribution of true and predicted labels. Precision recall curve: this plot shows the trade-off between precision and recall for different thresholds. ROC curve: this plot shows the trade-off between true positive rate and false positive rate for different thresholds. Fine-tune parameters. Classes: this parameter specifies the list of classes to consider. If not provided, the classes are automatically determined from the input data. Uncertainty methods. Confidence scores: each predicted label can be associated with a confidence score, indicating the certainty of the prediction. Challenges and fixes. Challenge 1: the multi-label binarizer can be inefficient for large datasets with a large number of labels, as it requires creating a matrix with a number of columns equal to the number of labels. Sample use case that resulted in challenge 1: a dataset with millions of samples and thousands of unique labels. Fixes to challenge 1: consider using a sparse representation for the output matrix, as this can significantly reduce memory usage. Challenge 2: the multi-label binarizer can produce a very sparse output matrix, which can be inefficient for certain algorithms. Sample use case that resulted in challenge 2: a dataset with a high proportion of samples with a small number of labels. Fixes to challenge 2: consider using a different encoding scheme that produces a less sparse representation, such as a one-hot encoding.